All right. Look at this. Back in action. What's up, everyone? I am glad to be here. Today, I am going to be taking a look at the Cassandra storage engine. This is going to be a little bit of a different kind of thing that I've been doing. Recently, I've been looking a lot at things that are coming in Cassandra 5, and that's been a lot of fun. However, I think it's kind of important to occasionally take a step back and go over some fundamentals. And what I'm going to do today is show you through kind of running an actual small Cassandra cluster how the storage engine works. The reason why I think this is interesting is, I'll be honest, like before I got involved with Cassandra, and this was 12 or 13 years ago, I read a lot about how it was built based on Dynamo paper, kind of this old kind of big table sort of data storage system. And I found it really interesting. I think that there was a lot of really cool things that exist in Cassandra, and it solved problems that I was really interested in at the time. Like, to me, these big scale problems are fun, and I'm in this really fortunate position right now where I've spent the last year pretty much working on Cassandra nonstop. Like this is what I've been doing for the last 12 years. I actually had to look it up. My first blog post about Cassandra and how time series works with CQL was back in 2012. I think I wrote the first article on how the storage engine works with CQL. So I've been doing this for a while, and to me, it was one of those things where, because I approached it from here's how it solves a certain class of problems, I knew about the storage engine and how the storage engine worked and how data modeling worked and how data was replicated before I even used Cassandra. And I used Dynamo before I used Cassandra as well. So I had some experience there. And so for me, moving to Cassandra, and I've always been a database guy. I was big. I did a lot in the MySQL community as far as writing and kind of tutorials and things like that for a long time. Before that, for almost 10 years. And so I'm just starting to show my age here. I think it's really cool. And so this week, I'm going to be doing a kind of an overview of some of the storage engine fundamentals. What I've discovered along the way in my process of using Cassandra at a small startup, to talking to people when I was at DataStax and The Last Pickle. I spent time at Apple and Netflix. And now that I've been independently consulting, for this project for the last year now, what I'm finding is that a lot of people that use Cassandra have a very different approach than I do. A lot of the times, people come and they start using Cassandra as developers, and I'm the kind of person that I always have thought about, like, how the database interacts with the computer, how it interacts with the file system, what it's doing on the CPU. And so I've always approached it as a little bit more like, rather than how I interact with it, how it interacts with the computer. And that's put me in kind of a different mentality than I think a lot of people end up doing. A lot of people come to it as a developer, they build their tables, they query things, but they don't really understand the ramifications of the queries that they're executing, the data models that they're performing. And I think a lot of people expect a lot of magic out of databases. Databases are not simple. I mean, they're complex pieces of software. They're some of the most complex pieces of software that that exist. I mean, an operating system is super complicated, and databases are too, because databases tax every single aspect of a computer. You can write some really interesting software. Oh man, I've had my music on the whole time. Music's off now. You can write some interesting software that is CPU intensive, but you might not uh, you might not actually like be taxing the whole thing if you're not doing IO and you're not doing things over the network. Like, so there's different classifications of problems. Some problems are very CPU intensive. Some problems are very disk intensive, and databases happen to be all of them. And distributed databases are kind of this super complicated thing because uh, you've got nodes talking to each other, you've got inconsistencies, you've got to deal with failures, you've got to deal with all sorts of stuff that's out of your control. And it's a fully asynchronous model for a lot of operations. Like, even if you're not aware of things happening asynchronously, they are. So a lot of fun, right? Like, databases are nuts, and distributed databases are really crazy, but they solve awesome problems. So this series today, I'm going to be talking about the storage engine, giving a brief overview as to how it works. And next week, I'm going to be looking at some of the newer features that are coming in Cassandra 5. So today, I'm not going to get into the weeds too much on specific features, but I will be talking about the storage engine in general and how data files work and what you see. And I'll show you some code. But instead of approaching it from just a, hey, I'm going to tell you about how this works, I'm going to show you using profiling and a running cluster, and I'm going to show you how you can do this yourself. So this is how I got really into the code base. So when I was working at the last pickle, I had to deal with a lot of like issues where people were like, we're not sure how, like, what to do here. And there's a lot of nuance. And so I ended up spending a lot of time reading the code. And the way I ended up reading the code, like, some people will dive into the code first, and then they'll navigate the code and they'll click through everything, and they'll try to figure out what's going on based on the code. I run the database. I use a profiler. I visualize my profile data, and then I use that to essentially tell me what to look at in the code base. So I don't spend a lot of time going back and forth and trying to say, like, oh, I think it's here. I know what's being executed. I know exactly what's happening because I've got profile data. So I'm going to show you how to do that. So if you're interested in getting involved in the project in a much more in-depth level, this is a really, really great way to do it. It's how I got into it. And I've learned a lot about how a lot of different systems work that I didn't write. Like, even though I'm a committer on the project, I've committed very, very little code. It's really not, I'm not the person that's writing a lot of Cassandra. I'm the person that is trying to understand it. I'm curious at how things work, but I don't have the time commitment to get into the code base and start writing stuff. So I'm going to show you my approach as a user, as a very, very curious operator, someone that wants to understand how things work and how to make it behave as efficiently as possible. And a really good recommendation here, Dimitri, for general background on how databases work. That book by Alex Petrov, I bought that book too. So even what's really cool here, I second that recommendation, by the way. That is a really, really good book. Alex Petrov is a brilliant software engineer and an incredibly wonderful human being. I honestly don't have a single bad thing. I don't have a single criticism of him. He is incredibly kind and patient and one of the smartest people I have ever met. So I definitely recommend that book. So if you want to get involved in database internals, thank you, Dimitri, for suggesting that. So I'm gonna just kind of give you a little bit of an overview as to how the storage engine works. I'm going to disappear for 1 second exactly as I fix my foot mat that I like to stand on. Hold on. All right, there we go. Foot mat is in place. Because I do my stuff barefoot, because it's nice and the floor is cold. So here is the deal. Let's start at the top. I thought about making some slides. I'm not doing slides. I'm going to do hand gestures. I don't know if this is actually taking a. Oops. I don't know if I'm going to get like a thumbs up, heart thing or whatever. Let's see what happens. So here is the gist of things. How requests come in. When you do an insert into Cassandra, the first thing that happens is that the data is written to an in-memory structure called a mem table, and it's written to a commit log. The commit log is your durable, and depending on some options, the durability is kind of up to you. The idea here is that we want to make inserts really fast. So Cassandra is based on the idea that we can essentially buffer writes before we write them to disk. A lot of databases, like a lot of relational databases, are built on B+ trees, and that's pretty cool. Like, not bad. The thing is that under certain types of workloads, building B+ trees on disk can be expensive. And so what we're essentially doing is we're treating Cassandra as a write back cache. That means when we write our data to Cassandra, we write it in memory, and then later on we flush it to disk. Okay, so this in-memory structure is called the mem table, and it's it makes it fairly cheap to write to. And the Cassandra 5, just as an implementation note, Cassandra 5 does have a new implementation of mem tables. I went over this a couple weeks ago, so I'll post later on in the description the link to the previous stream where I talk about new try mem tables and how they're different. And Dimitri was actually there and offer a lot of really good advice and knowledge. So I recommend, if you're curious about the new try mem tables, to kind of take a look and see some of the performance characteristics, because I was blown away by them. I was so excited. Anyway, so our write comes in, it goes to a mem table, it goes to a commit log, and that's it. Then we tell the user, cool, we got it, right? That's just at the storage engine level. There is, of course, replication. If you tell Cassandra that you want your data to be stored, like you want 3 copies of your data, and it will also write that data to the other nodes that are going to be responsible for it. There is something called a consistency level. That consistency level is when you do your write, how many nodes have to acknowledge the write in order for you to acknowledge, for the main node, the coordinator, to acknowledge that write to the user. So we're not going to get into that now. There's a whole, you can look elsewhere for that. There are a bunch of different consistency levels, and it lets you kind of slide things between highly available and strongly consistent, or you can even use some transaction level stuff, lightweight transactions. So now the user has now the user says, hey, cool, Cassandra got my write. It's sitting on a bunch of nodes. Eventually that mem table, that memory structure, eventually it's got to go somewhere. Like, you can't just have infinite memory. I think we know that. And so what happens is that mem table gets flushed to disk. It gets flushed to disk as something called the SS table. And SS table is it's a bunch of different files. So there's some people are not aware that an SS table is actually a whole bunch of files together, and it's not just one data file that has all of your stuff in it. It's actually a data file. There's a primary index. There's some checksum. There's a checksum file. Assuming you're using compression, there's a compression metadata file. There's a Bloom filter, which is used. It's a probabilistic data structure used for checking SS tables to see if they contain a partition. We're not going to get into that yet. So I think I went over everything here. We have compression, the actual data file, the digest, the Bloom filter, the index. Oh, a statistics file, which has just statistics about the data that was written. A summary file, which has it's a sampling of the index data is stored in this summary. So it's a much lighter weight version of the index. And a table of contents that just has basically all the files that were written. If you're using the SAI indexes that are in Cassandra 5, you'll also have some index components for each SS table. There's going to be some terms and there's going to be some other stuff. So there's a whole bunch of files. So every data file has a bunch of files. Now, I'm just going to bring up my screen here so I can show you this. Let's see, this version. Okay. And it looks like this is pretty small. So let's just enlarge my screen here. And let's say maybe that. No, let's maybe this. Let's see. Okay, hopefully that's fine. But you can see I'm already on a node here. And I actually also have, make this a little wider. I also have a workload running here. So this isn't going too crazy. This is only doing about 26,000 requests a second at 2.1 latency, P99 latency for writes, and 2 point something for reads. I've deliberately set it up this way. I'm not trying to kill this cluster today. This is just information. I will destroy a cluster, and I will destroy the cluster next week, or try to. So let's just take a look. So if we go here, and this, by the way, I feel like it's important to say this. This tooling, this cluster was created by my tooling called Easycast Lab. I'm really proud of the work that's been done on here, and there's been a few other contributors to this recently. Jordan West, who's a fellow Cassandra committer and is working with me on Cassandra training. He's been adding a lot of really cool features here. We actually just added EBS support, which is why week 3 of the storage engine, we're going to go into optimizing Cassandra on EBS. So if you're running Cassandra on EBS and you're interested in learning about how that works, week 3 is going to be really interesting to you, especially since I'm going to be covering it from an optimization standpoint and looking towards the future optimizations that can come in Cassandra. Someone's got to do the work. So this is partially a sales pitch. So if you've got a big old budget and you're looking for to run things in better on EBS, give me a call. Maybe we can do some stuff. Anyway, so this was created with Easycast Lab. Easycast Lab makes it ridiculously easy to set up a cluster. So if you look, let's see. So here. So the first thing I did was call Easycast Lab init -C. That means I want -C3. That means I want 3 nodes. -S1. That means I want 1 stress node. And go ahead and bring it up automatically. It uses Terraform behind the scenes. It actually talks to a Terraform Docker container. And basically creates this, and then I edited my this Cassandra patch.yaml file. This is a fragment of a Cassandra YAML that's applied to the environment. So this comes up automatically. It automatically sets a bunch of 2 kernel parameters. This allows me to do my performance profiling. It does a whole bunch of this fun stuff. Make sure that we are allowed to do a whole bunch of mmap operations, mount the disk as XFS. What else do we do? Automatically sets up axon ops, but that doesn't work for Cassandra 5. I really like to use that for my dashboards. And then basically it takes this is the fragment of the YAML, pushes it up and uses a tool called YQ to patch the YAML that's on the server. So instead of having to edit the whole YAML, I literally just change the things that I want to change, and it just does that for me. And then let's see. So then it goes ahead, updates this. Anyway, enough about that. So, and then I started this workload. So this was like up and running in like 5 minutes. So I started this cluster this morning. Like, it wasn't a big deal. The data directories are automatically configured for you. And so we have, you can see here that this is set up on Mount Cassandra, and I'm writing stuff now. I've only used 5 gigs of data. This is a very, very small workload. And it's a 50-50 read-write workload. So I'm actually going to show you a little bit about how the storage engine works from the read path and the write path. Anyway, I was talking before about the writes. So the SS table gets written to disk. So let's take a look at that. So here you can see that this is Mount Cassandra Data, the name of the key space, which is Easycast Stress, and then the name of the table along with the UUID. And then we've got all this stuff. So my data has been compacting, which I'll talk about in just a moment. But these files here, compression, info, data, digest, filter, index, statistics, summary, table of contents, those are the components that that are with this SS table, which is number 153. So each SS table is going to have a different identifier when it gets written. Traditionally, there have just been monotonically increasing numbers here. So you'll see this is 153, 154, 155, 6, etc. This is cool, but presents some issues if you want to do like importing data from one cluster to another and with the same names, and all of a sudden you've got conflicting numbers. The newer versions support the ability to use UUIDs instead of the numbers, and I didn't turn that on here. Most people are not going to see that yet, because I doubt you're running Cassandra 5. They had to do a reverse engineering to support it. Was that regard to my the numbers? I'm not sure how delayed you are. Feel free to clarify. Let's see. So we've got this, and one thing you might notice is that this number is already at 153. Oh, check the previous comment. I don't see a previous comment. I see this. I see this. And I see this. That's it. I don't know. So now that we have the data that's written to disk as SS tables, there's a process called compaction. So if we were to just be writing SS tables to disk, eventually we would have a lot, right? And if you want to do a read, you have to read the data out of these files. And if you have to read the data out of a lot of files, it can actually be pretty time consuming, like doing a bunch of IO. You want to minimize, the database should minimize its IO. Even though NVMe drives are really fast, and like when I say fast, I mean like they're nuts, like over 2 gigs a second of sustained throughput at 100 microsecond latency is incredible, like just mind-blowing tech. However, you don't want to be wasteful, because you can still incur performance penalties. You can still oversaturate an NVMe drive. I've done it. I've seen it done. It's not impossible to do. So what you want to do is merge these files together over time. And that process is called compaction. So as I notice how this first time I did the listing, it was 153, 154, etc. And I just did another listing. And now it's 161, 162, 164. So the really interesting thing about compaction is that there is no one setting that can work for every single type of data pattern that you have. For example, if you write time series data, it's a different shape of data than if you have a key value workload. Like this is a key value workload. There's 100 bytes per record. You could think of this as like a user table would a key value table is like a user table, right? You've got users profile data, but you don't have a lot in there. Fairly small records, cheap. You read them a lot. Maybe you update them a decent amount, but in this case, you probably don't do 50-50 reads to writes. So there are different compaction strategies that can be optimal for different workloads. Traditionally, we've relied on, when I say traditionally, I mean like let's take the last 5-6 years. There are three that have been the most popular to put into production. Size tiered compaction is like the like OG compaction strategy. It's been around for a while, and it's actually the default. If you create a new table, it's going to be the default compaction strategy. The thing is, it's not great. Like it's kind of a crappy compaction strategy for most use cases on modern hardware. So I never recommend it, or almost never recommend it. It's really great if you've got like tables that are not time series, but you still have a lot of values for a particular key. Now let's talk a moment about what that means. When you write your data into Cassandra, you can, whoops. Oh, come on, there we go. Let's say I look at this table here, Easycast stress. And let's look at the tables here. Okay, so it says key text primary key. Okay, and by the way, I'm just going to really quickly change the workload that's running here, so I have a new. Let's just go ahead and run this for a day. So I'll just fire this off. So I don't. This one's going to do. It's going to aim for 5,000 queries a second. So this just has this thing called a key and a value, and the key is defined as a primary key. Coming from a relational world, this looks pretty normal. This is one of the things that is like a very, very basic table. However, if we look now and we see that we have this random access table, the partition key, the primary key is different. The primary key is down here. Okay, so we have our partition ID, we have a row ID, and we have a value. The partition ID, this is this first value right here. So this primary key is a tuple. The first record in the tuple, and it could be another tuple, by the way, is your partition key. Let's just take a quick look at the data that comes back. Let's see. Let's just do a quick on that. I would argue that STCS might also be a good choice when you have time series data but cannot use TWCS. Yeah, if there's a reason why you can't use TWCS, like if you're on a really old version of Cassandra, or if and keep in mind when I say time series data, I'm that's kind of like a shorthand. If you're updating or deleting your data, I don't really classify it as time series. Time series is generally immutable. There are cases where it's not, but I kind of just offhand will refer to time series as immutable time series. So if you have like some sort of like data enrichment, for example, then you'd still, I guess you'd still classify that as time series. You write some data, you go off, you do some other things, and you write updates to it. That's still reasonable. There are very few time series cases that I can think of where you wouldn't want to use TWCS. If you weren't deleting, or for example, if you didn't put a TTL, then you couldn't use it safely. Oops. Oh, hold on. I was thinking about a situation where retention periods are not predefined. You want to keep data for a very long time indefinitely. Yes. So Sebastian, I argue that there's a much better way than using size tiered compaction. I would create a table per like month or week, depending on the frequency of the data, depending on how your data is accessed. I would always rather create a table per month. So I'd have time series 2024 April. And when I know that I no longer need that data, I would drop that table. The little fun fact, I wrote a paper or a blog post a long time ago that was called Massive Time, Cassandra, what was it, Massive Time Series? I forgot the exact name of it. And I even did a stream where I talk about that. And I advocate very, very strongly for putting table per time period for that exact use case. And it was implemented at Netflix for the time series data gateway for cost savings of 90% from people doing it on their own. Unfortunately, Cassandra does not work well with a large number of tables, so we should be careful here. That's true, and that's why I advocate for per month, because 12 tables is fine. You also only have one or two at the boundary, at a month boundary. You only have one or two tables that are actually active. So one of the real problems with Cassandra is if you do have a lot of tables, like if you were to do a table per day or a table per hour, that would be terrible. Table per month, you're going to be fine. Even if you go for 5 years and you have 60 tables, who cares? If you have a whole bunch of these in a single cluster, then that becomes a problem. I would advocate for running multiple clusters for different use cases. Never do a mega cluster for everything. That's just practice. At least I classify it as bad practice. If you want my advice as someone that literally just deals with people's broken Cassandra clusters all the time for the last half decade or more, that's my advice. I don't care what anybody else says. So let's go ahead and just look at this. Okay, so here we have this. This is one record out of here. We have a partition ID, we have a row ID, and a value. So doing query with limit 1, this doesn't really tell us a lot. But if I were to do this way, oops. Okay, so I get these 3 rows back. Now, the interesting thing about this is that these rows are actually stored on disk in this order. So in the SS table itself, assuming that we were dealing with 1, and let's just, I'm just going to qualify here. There is you will get results that come back from multiple SS tables. If we do, okay, so I just did that read. This is Easycast stress random access. Okay. Okay. So when I look here, I can see that we've only had to read the data out of one SS table. So in this case, all of the data for this query would have come back from a single SS table. And that means that all the data was stored in the SS table in that order. You can store it in reverse order if you want, but you can't store it in arbitrary order. So the ordering is determined by this second. So this first part is the partition key. Remember, this can be a tuple or just a single field. And then it's stored, the remainder of this, these are all clustering columns. It's stored in those order of those columns. So row ID first. So everything is sorted by the row ID. That's why we get row ID 0, 68, 71. You'll always get it back in that order. And what's also kind of interesting here, if we were to go back and like rerun this query, right? If you were to try to do it by something else, you can't. That's because Cassandra was designed for humongous amounts of data. Like there are clusters all around the world that have hundreds of terabytes or petabytes of data in them. It's pretty nuts. You can do some really wild stuff with this. And so you can have technically some fairly large partitions as well. And by that, I mean, you've got a lot of rows. Each one of these is a row and they're within a partition. So if you're familiar with a relational world and you just think about rows, now you think about a table, and within the table, you have partitions. Within partitions, you have rows. And the rows are sorted. And we don't have sorting options here because the sort is potentially really expensive. And we just, so far, there hasn't been a lot of interest in trying to add unpredictable sorting, because there are people out there that put tens of gigabytes of data in a single partition. So sorting that would mean that you would need to allocate for the entire data set and then sort the whole thing and then return it. And we're not trying to be an analytics database. We're literally just trying to get you some data as fast as possible in a predictable manner. So in order to do that, we rely on the sorting on disk, and that's what allows us to achieve good performance without necessarily having unpredictable overhead of maybe we sort 5 things or maybe we sort 5 million or 5 billion things. So that's why that exists, and that's why those limitations are in place. Maybe one day we'll support it. I have no idea. That's not a me question. That's for someone who's probably smarter than me. So anyway, what we can do now is, so we know that our requests come in, they come to the mem table, they're essentially buffered there, they're written to the commit log, they're written to disk as an SS table, and then we have these different compaction strategies which allow for sets of SS tables to be picked and merged together, and then they get written out into new ones. They might be written out into one, or they might be written out into multiple. So another strategy that I talked about a little that I didn't get into was leveled compaction strategy. So leveled is pretty cool. This was based on, I'm forgetting the name where this came from initially. Whatever, I think it may have been, I don't remember. Doesn't even matter. But the idea is that we, instead of just grouping together level DB, thank you, Dimitri. We have, so size tiered compaction strategies takes SS tables that are similar size, buckets them together, and then compacts them together and writes them out. Leveled compaction strategy has this idea of levels. Data is written into L0, and then it gets compacted together. And as SS tables, as you get more and more data in a level, it gets compacted together and promoted into a new level. Level compaction strategy will actually write out multiple SS tables. So it's sometimes people think, hey, we're going to compact things together. We write out one SS table. Not the case at all. In fact, most of the time, most compactions running in the world right now are writing out multiple SS tables. So leveled compaction strategy is really nice for use cases where you've got a lot of reads or you've got a lot of deletes or updates, because it will actually keep a partition in a fewer number of SS tables. So remember, here's one thing that's really important. Not only is the data within a row sorted, but there is a predictable sorting to the data in the SS table. It's sorted by something called the token. So you will essentially, if you have, let's say, 10 partitions in 2 SS tables, they'll be stored in the same partition ordering. And so what you can do is you can scan through them, and as you're looking through partitions, you can write them out into the new SS table, and it's actually pretty efficient to do it that way. There is a new compaction strategy that I took a look at a little while ago called Unified Compaction Strategy that allows you to pass parameters to make it behave like size-tiered compaction or like leveled compaction. And it's pretty cool. I actually, am I using that here? I think, oops. What am I doing here? Use Easycast Lab. So I'm using that here, and just real quick, I'm gonna break out here. I'm just gonna take a quick look at this patch. So one thing that's really nice, I'm not even sure when this was added, to be honest. Someone might know. What you can now do is define your default compaction strategy. So if you're an operator and you're sick of people creating size-tier compaction strategy tables because they just leave off the compaction, you can set a default here. So this is set to automatically use the level of the compaction strategy. I really like this. This makes me quite happy. I'm happy this got added. Let's just go back here. Okay, so here we see that we're using the leveled compaction strategy. So this is coming in Cassandra 5. My testing on it, I've only had positive things to say. So like the try-mem tables, try-mem tables are just, from what I can tell, a strict improvement from the on-heap mem tables. Like it's just it's a lot better. So where am I here? So we've got data that's in multiple SS tables. When you want to do a read, it has to read a bunch. It has to read the data from the SS tables that have it, merge that stuff together, and then the result comes back to the user. So if you have a lot of SS tables, it's got to merge data from potentially, if you have, let me just qualify this. If you have a lot of SS tables that contain a particular partition and you query for that partition, it will have to read more SS tables, which means more IO, which means worse performance. NVMe can mitigate some of this, but I really do not like doing that. I really do not like using hardware as a crutch to deal with bad choices. Let's say it that way. So now that we've talked about that, so I've talked about how writes come in, how they're written to mem tables, how they're written to SS tables, the components of the SS tables, and how compaction works, and briefly touched on reads. One thing that's useful to know is that you can't, without a secondary index, you cannot I cannot search for something with this arbitrary value. You can if you do this. Let's see. So remember, we can't do that. So let's just do that again. So here we have this value. So this is just a random string. If I try to do this, same thing. Doesn't allow it. Okay. But if I do this, it will run, but you do a full table scan. This can be potentially really expensive. And you can see here, it's just like, doesn't even want to do it. I hit a read timeout, I think, on, read failure. So it's not even going to get through it. So you really don't want to use a lot of filtering to do full table scans. It's not good. Moving along, let's now take a look at what's actually happening from a code perspective, because this is where things get a little wild. So I'm just going to exit this node. And by the way, like, let's just take a look here. I want to see. This isn't using too much. This is hardly doing anything resource-wise. If we let's do that. You can see here that we're only using 10% of our CPU. So we've got 5% here, 2.5 here, a little bit there. Okay, that's not bad. So this is really not a lot. I'm going to go ahead and actually increase this. So jump back on here. Let's do this. Let's watch. So let's bring this up to a really, really high. Let's say we're going to aim for 100,000. I don't think we're going to be able to do that. If I put 50,000, we're probably not going to love it. But let's just give ourselves a. Okay. So what I'm doing here is I say, hey, like, let's go ahead and we'll run this. I want 50,000 queries a second, but don't exceed 20 milliseconds latency for reads or writes. So this is interesting to me because I like this. Oops, what did I do? Oh, forgot a dash. On the fly debugging. Okay. Apparently I'm. What did I do here? Rate 50,000 max RLAT. On the fly debugging failed. So this says my max RLAT. It doesn't like that. Oh, I know why. Because I spelled it wrong. On the fly debugging again. Okay. So this is going to ramp up. So there's a quick warm up period. While this is running, let's just go ahead and watch this. You can see how CPU usage is going to increase. Oops. CPU usage is going to increase a little bit over time. We might see a little I/O wait, but again, we're probably not going to see a lot because it just doesn't really. MEMs are nice and fast. So let's put that over here. And now we will do this. Run a tool called C. Oops. So I run a tool called CFlame. So if you haven't watched this before, I'm a big advocate for flame graphs. And so one of the things I've done with Easycast Lab is make it so that it's really easy to get flame graphs from your cluster. So you create your cluster, and then it drops a file in place, and it says env.sh. Running default compaction option. I have checked. Is it an added 5? Okay, cool. I'm glad it is because probably most people will want to use UCS. I should go into how UCS affects things later, but I want to get more familiar with some of the technical details about it. But there's a few things I really like about it, especially the fact that it's friendlier for streaming. Anyway, flame graphs. So what we have here is a really convenient way. When I do this source env, it sets it up so I can SSH into things real quick. It actually sets up like a local SSH config for me, and aliases, my SSH command to use that config. It's pretty awesome, if I say so myself. But it also adds a tool called CFlame. So CFlame I run locally. So this is on my machine right here. This is CFlame. I do Cassandra 0, and if I just do this without any arguments, it runs a CPU flame graph. So a CPU flame graph, what we do now is it takes a 30-second sampling profile of this Cassandra process. So on the node, there's actually a helper script that figures out the process ID of Cassandra and then calls a tool called Async Java Profiler, which attaches to the Cassandra process for 60 seconds, takes the CPU profile by sampling. So it has very, very little impact on the actual performance of the node. What it does is it samples the stack traces, and then at the end, it takes those stack traces, and depending on the frequency that certain frames were hit, will draw a visual representation of that, of what was going on. CPU flame graphs are really, really helpful because you can tell where your time is being spent, what functions are taking up the most time. The only thing that, well, not the only thing, but one thing that you need to remember here is that CPU flame graphs do not take into account threads that are not actually running. So if you have a thread that's sleeping, you won't see it. If you have a thread that's waiting on something, you just won't see it. So only threads that are in the running status. So if you want to start messing around with flame graphs, it's really important to understand that, because you can miss stuff. You can miss a lot. So you need to use a combination of CPU profiling and wall clock profiling to understand where your time is spent. Anyway, so this is the file that I have here. So I'm just going to go ahead. I'm going to bring this. I'm going to open this. So I'm just going to open it up, and then I'm going to switch to that window. Let's do. So it does the flame graph, and then it automatically downloads it for me. So now it's already downloaded locally. Cassandra 0. So you can't see this yet. So let me go to it. So this is where things start to get pretty fun. So I'm now going into the storage engine, and so here's a visual representation of what Cassandra was doing for those 60 seconds. Remember, it's a sample. It's a fixed rate sample of what was happening on the CPU. So it's not perfect. There is if something happened and it happened to not get caught in the stack trace, like it happened that infrequently, you won't see it here. Probably not that big of a deal because it's not taking up a lot of time. Sampling profilers are awesome. I love this. I have figured out what's wrong in hundreds of environments. So using this, so including some of the testing that I do for Cassandra releases, because I like to, as if you saw my previous streams for Cassandra 5, you would know that I just mess with this stuff and I break it because it's fun, and this is what I do for fun. Weird. So here we can look for read. Okay, so we've got some stuff here. Where is my reads? So let's see. Oh, select. That's what I want. I want to select. Helps to know what you're looking for. Am I not selecting? I am selecting. It's not that. That can't be right. So these are our writes here: modification, storage proxy, mutate. That is a lot smaller than I was expecting. Oh, I know why. Because I didn't pre-populate this table. So this is one problem with doing things on the fly. So I'm just going to kill this workload here. I'm going to switch back to my previous one, and I'm going to take a new flame graph. Random partition access, because I didn't pre-populate the data, it's it's really, really cheap to try to select data that doesn't exist. Big surprise. But Cassandra has a whole bunch of checks in place that make it so that you don't have to do unnecessary IO for where's my terminal? There we go. You don't have to do unnecessary checks. So this is now running again. So again, we call CFlame Cassandra. Fortunately, I pre-populated the key value workload. I did plan that out. Wipe the sweat off on the spot. So you can see here, this is like only running at 12% idle. So this is a pretty decent workload right here. We've got about 20,000 writes a second and about 20,000 reads a second happening here. And so now let's get our flame graph. Let's see what this looks like. So let's do two things. We're actually going to look at the code path for mutations, and we're going to look at the code path for reads. And I'm also going to show you how to isolate this stuff. So when you do these flame graphs, it can be really helpful if you know what you're looking for. If you want to see something specifically in one code path, I'm going to show you how to get that, because like you just saw, like I was like, where is this? Like, where is my select? So I'll make it I'll show you how to do that. That'll improve things. Again, if you're looking to get into the storage engine, this is how you do it. At least I think. If you were to ask me, all right, let's look at this. So, and I really need to get this figured out so I can swap my screens. I say this every time. I'm going to stop saying it. From now on, I'm just going to, oops, wrong one. Boom. There we go. Okay. So here we are. This looks a little bit different. So see this right here? This is query processor. We're not seeing it over here. This is compaction over here. You can't, I kind of moved over it really quickly. This is compaction. This is where the CPU time is being spent, because it says here it's really small, but it says compaction task. So we don't want that. What we want is this right here. Do we want any of this? Single partition read command. Okay, so single partition read command, mutation. So there's some stuff over here, but what we actually want to do is see things that were the result of something on the interacting with the user. So before I continue, let's just get another one, because this is fun. I like my flame graphs. Okay, back here. So we'll do the same thing as before, CFlame Cassandra, but we're going to say -I for include, and then I'm just going to pass this. Remember, I noticed, I mean, I know, but I noticed, you would notice if you didn't know before, that the read commands and the other commands that are being run are a lot of it's coming off the SEP worker. All of it is coming off the SEP worker. So what I'm doing is I'm passing this -I flag, and I'm saying, hey, let's only look at stuff that's on the SEP worker. So the SEP worker stands for shared executor pool. So Cassandra basically has a pool of threads that, instead of having a bunch of different thread pools for a bunch of different tasks, there's one thread pool that's shared for a lot of tasks. And so when we need to do work, it takes out a thread, gives it a name, and you can see those names if you go into like htop. Oops. So if you go into htop and you go down here to display options, if you do show custom thread names, you'll actually be able to see it. So now if I go here to my Java process, I can see that my GC thread is here. And if I sort by CPU time, this is just a really helpful tip. You can see that, oops, go up. Okay. You can see where your CPU time is being spent just at a high level. So if you take a look. Now, one disadvantage of the SEP worker is that by renaming threads, there is a little overhead on there. And certain tools, if they cache thread names, you can end up mislabeling your threads. Like it can mislabel. So when you read the name of a thread, if you do like, if you read the name of a thread and then you like are checking on it periodically for how much like CPU usage it's using, you'll discover that it might not be doing the same thing anymore. So you can't really rely on the thread names as a permanent thing. I'm actually considering, and if I don't know if people find this interesting, but please leave a comment if you do. I'm considering doing an experimental build of Cassandra where I change a bunch of things to work how I think I might want to see the database operate. One of them being using cached thread pools for reads and writes instead of the SEP worker, getting Java 21 support for generational ZGC, and some other IO things that I'm actually going to talk about in week 3 and 4. There's an option to disable renaming. Wasn't even aware of that. All right. So now I forgot to run that. CFlame, SEP worker, go. So now this is going to go ahead and run this. Now we're going to get a profile that doesn't have all the other stuff that's going on. It's literally just going to be the workers. We're going to take a look at that. The other reason why I'm curious about the thread pool stuff is because with virtual threads and it might be reasonable. So even though that the thread pools are efficient, creating lots of threads, like thousands of threads, each thread has overhead. And so if we were to use a cache thread pool, things get a little bit more efficient because we have fewer threads and they get reused. That's similar in design to the SEP worker now. In fact, it's almost exactly the same as it is now. If we were to just use one thread pool, one cache thread pool, it might actually be a decent drop-in replacement for the SEP worker. SEP worker was written a while ago, back for Java 8 or Java 7. And at the time, my assumption is that there was inefficiencies found in the internal stuff, but I don't really have the history of that, to be honest. That's been in there for longer than I've been looking at the code, so I don't really know. But I am curious to see if we can kind of get rid of some custom thing. I don't know if we need the custom thing anymore. Step worker might be still great in comparison. I really have no idea. Anyway, let's take a look here. I don't know if you can hear snoring in the background. That's my dog. She is a sweetheart. I'll start putting her up on the screen. Yeah. Okay. So let's present. Stop the screen. Once again, switch things up. Okay. Cassandra and Nettie uses thread local quite a lot, and thread pool is expensive virtual threads. Oh, good to know. Hey Dimitri, I'm going to plant an idea in your head since you know a lot of the internals. Java arenas are in preview mode. What if each SEP worker had a thread local arena that was deallocated essentially at the end of every request, and all the requests everything that happened for the life of the thread as it's out of the pool goes into the arena. And then when it's done, the whole arena can go away. Think about that. And let me know. Maybe it's a terrible idea. I've never tried it. Anyway, so here's my claim graph. So if you're interested in the storage engine, this is how you figure it out. Do I mean native memory arena? I don't have the hold on. So I'm referring to this. So yeah, the native so using this. This is what I'm referring to. Yeah, what I'm interested in doing is saying like, hey, like if we know that a thread comes out of the pool, whatever gets allocated in that thread should be allocated in that arena, and then when it's done, when it goes back in, we just dump everything out of it. Who cares? I'm quite curious if that would have any performance advantage, because there's really no reason to allocate all this stuff into the main, into the heap with everything else. So if you could limit the allocations for the lifetime of the request, an arena, it seems to me at least, like, my stupid brain makes sense at a high level. I think it could be fun. Anyway, so we've got the SEP worker here. And as we go up, so let's just take a look here. Oh, I'll try to think about it. Yeah, man. Dude, if you want, ping me on Slack, man. We should talk about this. This is actually pretty cool. I'd love to, if you're interested in collaborating on it or anything, or doing a test version of it, and then we can test it on this stream. Like, we could do that. We could talk about it. I'd actually love to do some collaborations like that, because I think this stuff is really fun. Yeah, I'm a nerd. So let's look at each of these stacks. So if I zoom in here, I can see that this says mutation verb handler. Okay. So that's that one. This one, I can see that this says single partition read command. This over here, I can see that this says query processor process prepared. So there's different stages. So one of the things about Cassandra is that there are, it is a CEDA architecture, which is, stage event driven architecture. Blanked on that for a second there. Basically, there's different thread pools that do different things. Sometimes we have a thread that comes in. You have a request, and there's a native there's a native transport request thread pool. It says, okay, cool. Now I got to do something with this, and it hands the work off somewhere else, and that hands it off somewhere else. And basically, we're always handing work off. And the idea is that we don't have like one thread doing everything. It lets us control resource limits. There are definitely some interesting advantages to doing it that way. Is it perfect? I have no idea. Is there a better way to do it? I'm sure it can't be. There has to be, right? Or there's probably tweaks that we can do to continue to improve things. It helps to know what it's doing. So what we have here, this says, this goes to, so SEP worker, and then it says transport dispatcher process request. So if you're interested in following the request, if you're like, hey, I want to figure out like how does a write happen in Cassandra, this is how you figure it out. In fact, this is you can see if we go up the stack here. Can I make this bigger? Awesome. Okay, hopefully this is easier to read. I need to figure out how to like zoom on stuff, but when we go here, it says dispatcher process request, transport message request execute, and then we go up here, query processor process prepared. So if you're interested in following the lifetime of the request, what I've done is I've taken a profile of a running node that's doing reads and writes. I've visualized it as a flame graph, and now I can step through all of the individual frames that have been aggregated together and essentially give me a view into what the database is actually doing. So we can look through anything. You can look through compaction, whatever features you have enabled, you can do this. The really cool thing about this is that the width of the flame is a visual indicator that helps you understand where the time is spent. And I'm going to show you a little bit more about this in just a moment. Because if you're trying to do some performance tuning, there's a couple different things that we can do here to make it even more useful. However, we're just getting to know the storage engine. So here we go to query processor, process prepared, process statement, and then this branches into a couple different areas. We see this modification statement.execute. So if you're interested in figuring out how mutations occur, you're going to go down this path. Mutation, modification, execute, storage proxy, mutate with triggers. That goes up into mutate. That goes up further to perform write. Now we're at the point where the storage engine is saying, okay, there's a bunch of stuff that we have to do. One, we need to figure out what other nodes own this data. That's this stack right here. That's where we say endpoints for token. Okay, so it figures out what other nodes own that data. And this is actually pretty cheap. So this perform write is only taking up 3% of, and remember, this is just the coordination part. Perform write basically is only taking up 3% of the CPU time. I can see it at the bottom of the screen here. You can say, storage proxy, mutate, 6.58%, perform write. This, oops. Why is it not? So it goes from mutate 6.58 to perform write. So there's some, oops. Okay, so something else happens along the way in mutate potentially. There could be a GC pause. It really depends on it's a little interesting that these are different percentages. Got to dig into that. Anyway, locator over here, and then this side of things says storage proxy, send to hinted replicas. So this is the core data path. Okay, I can tell because of what it says that it's doing. The send to hinted replicas, this is something coordinator does. This isn't a storage engine internal. So I say, okay, cool, let's back out. What else is going on? Then we have, so that was this the first stack? No, that was this one. So that was the CQL query processor. Okay, so that's this. So a lot of this time, 25% of the time was spent here. Then we also have this stack. So let's investigate this guy. So this is our read path. I can tell because it says read command. If we take a look up this stack on read command, we can see all of the functions that get executed. In fact, we can go all the way into the file system. So when we're using the asynchronous Java profiler, we don't just get the Java frames, we also get the frames from the OS. So these are system calls right here. System calls are in orange. So here we go. So the red is a native library. I believe the red is a internal to the JVM, and then these go into orange goes into the syscalls. So we say, hey, read command, execute locally. Okay, so this is our local read. Single partition read command, make row iterator, big table reader. So if you want to go into the storage engine, if you're really curious to go down to storage engine to the point where we actually touch the disk, right? We can see that's happening here. So we go, okay, cool. What is this? Well, boom. This is called, oops. This says compressed chunk reader. Well, I'm using compression. That makes sense. So what does it do? Well, first of all, it's going to decompress some stuff. Okay, so it's going to call this decompress. And by the way, the ordering here isn't important. It's not left to right. When I say first of all, I just mean the first thing I'm seeing. It's not decompressing the data before it reads it. It's actually reading the data first. So compressed chunk reader has a thing that says standard read chunk. Okay, that is going to call this channel proxy.read. Okay, so as we go up, we hit channel proxy.read, and then we move into the JVM function calls. Now we're into file channel implementation read, read into native buffer, and eventually we hit pread. Okay, so now we're actually starting to go to the file system. Then we hit this entry syscall, do syscall, VFS read. So VFS read is actually hitting the virtual file system. So one thing that's really interesting to know is that all the operations that happen here are against the virtual file system. The virtual file system sits on top of XFS, ext4, whatever you're using. Side note: don't use ZFS. I've been dealing with a ZFS headache and recently. Had to write a custom patch to figure that out. ZFS, no bueno with Cassandra, at least not with Ubuntu 22. Tip. So VFS read, and then you can see here it says XFS file read iter. So now we're in kernel internals. So now we can take a look at what's actually going on in the file system. If you were interested in following this all the way down to the kernel, you can do it using this. Like, to me, this is amazing. So we also see that, like, we can go, what else do we have? Security file permission. So this is actually checking to see whether or not we can do it. I won't go any further into this. I want to get through the rest of these stacks, and then I'm going to wrap things up. So we're back here. So let's see now. This storage proxy mutation apply. So you'll notice try memtable. That's right. I'm still using it. I'm using it now. It's if you're using Cassandra 5, I'm like, let's go try memtables. It's great. Let's see. So we go up here, key space, apply, internal, column family store apply. Now, one thing that's kind of interesting here, because of Cassandra's history, we didn't used to always call these things tables. We used to call them column families. And that's a holdover from the big table days. I don't love that. I don't love it at all. I actually really kind of bugs me how we have internal things that are called column families. I wish it would go away. I even put a Jira up and then just never followed through on it. I wanted to rename things, but I think it's one of those things where it is, for a lot of other people, it's more of an annoyance than it is for me. I'm a bit of a stickler for some things. Anyway, column family store apply. So when we do our, let me back it out a little bit. Oops. Okay. So column family store apply is going ahead and it puts the data in the mem table. So that's what this is doing. So we're blocking on that. We can see that there is an interesting path here. You'll notice that it says put recursive, etc. It's recursive. It's recursive algorithm. So hopefully this doesn't get too big. That could could get a little crazy if it got super deep, but it doesn't seem to be too bad here. So if you're interested in looking at the try memtable implementation, you can go. You would want to start here. It's org Apache Cassandra DB memtable try memtable.put. And that's, to me, it's pretty cool. Like I'm always curious, but I don't have a lot of time. Like I'm literally just like, I barely have any time to get anything done. So this is what I do. And I'm like, how does this thing even work? Do I want to follow? Do I want to open up the code first? No, I want to look at this, and then I can go, okay, cool. Like now I can get familiar with the part of the code that I care about. So we can go up here and try memtable, put recursive. What's going on here? Bunch of TCP related stuff. What is going on here? TCP. Why would that happen that might be an alignment. That actually might be an alignment issue. So there are some times where you're going to get some weird data out of here. The async profiler will try to match up your the underlying perf data with your Java stacks, and sometimes it doesn't do it perfectly. It's a known limitation. I seriously doubt that that the try memtables are doing any TCP activity. So I'm just going to disregard that. And this is that only affects the matching side. It doesn't affect the actual Java frames. Okay, so we back out of that. So now we've taken a look at how the what happens when you execute CQL. Remember, it goes through that transport. You can take a look at all those frames. Dispatcher, process, request. Okay, you can then take a look at your storage proxy, single partition read command, query storage, query memtable, and disk. You can read up on how this data is fetched and aggregated together. Remember, one thing I didn't explicitly mention before, but the memtable data and the SS table data is merged. So when you do a read, if your data is sitting in the memtable, you're not going to just not get it because it's not an SS table. It does read the memtable data. And then it gets returned to the user. And then here, what's this last thing? I know I already looked through this one. Okay, saw that already. Mutation verb handler. All right, I think I've gone through everything. I've talked about writes. I've talked about I talked about writes because we hit the memtable path. Talked about reads. We have the single partition read command. And I've kind of given you the overview. One last thing that I will do before we stop here is I will do a different kind of profile because I'm going to look for anything that I'm going to do a wall clock profile. I'm going to do wall clock profile of compaction. This is a different, and you know what? I'm actually going to go and just show you an advanced move. So this is a wall clock profile of the compaction process. I hope, because I don't know if I typed it wrong or something. So what we're going to do is wall clock profile is different from a CPU profile. If a thread is sleeping, it will not count towards the CPU profile. If it will count towards a wall profile. So what you'll actually find is that if you don't do some of these little tricks, you will end up with a graph that looks insane. Oh wait, I'm not even showing the thing. Hold on, let me get to this. There we go. Okay, so what we have here, and I'm just going to put this. I'll put this on the screen so everybody can see this. Let's go with this. Boom! Awesome. I hope I'm doing this right because otherwise it's going to be a little bit embarrassing. Wall clock profile will include threads that are sleeping. So it turns out when you have thread pools and you have lots of threads and most of them are just chilling, you will end up with a graph that doesn't make any sense. I'm not going to show it right now. I don't have time. But basically what we're doing is we're saying -I, that's going to include anything that mentions compaction. -X is going to exclude anything that says park. In fact, we're just going to change this to unsafe park. And the reason why is because this right here. So see how this says 40% of the time was spent in unsafe park? We don't need to see this. It's not helpful in this run. You will actually see a lot of time spent in unsafe park. This is my main gripe with the SEP worker is under low load, you will see it use a lot of CPU. It actually has they do a lot of system calls. And I don't know if we're going to see the same thing out of any of the internal pools. We probably do. I'm sure that if we use a cache thread pool, we might see the same problem. So this may not be a unique thing to Cassandra or to the SEP worker. Anyway, so let's go ahead and run this. So we're saying include compaction, exclude unsafe park, and we're going to do a reverse flame graph. So reverse flame graphs, if you think about the way that the one that I already showed you, the stack at the bottom is broad, right? It's all of the things. It's the main thread that was running, right? The main method, and then you go up, right? And it's maybe there's two above that, so it splits, right? So it's kind of like it's a flame. That's why the things goes like this. But we can also do it in reverse. So let's suppose at the very, very tip of these flames, we had something that every time it was called, let's say that it was taking up like 3% of the CPU and it happened 10 times. You wouldn't notice it as much because it'd be at the tip of the flame. But if we do reverse, then we actually get to look at this from the opposite perspective. We get to say, hey, like let's add up all of the time at the tip of these things where our time was spent, and then do an icicle graph, and we'll show us how we got there. So the same code can be reached by multiple code paths. We're actually gonna show it as if it was reached by one code path, but then split it up by the code paths that it reached to. So, oh, come on. Of course I did it wrong. Okay, I'm gonna update my thing. So here, this is actually what I'm doing. Okay, so now I'm doing that. See if I did it wrong again. Okay, so now this is, did I spell? Oh, I see. Put that in the wrong place. Okay, so now I gotta update my thing again because maybe I'm gonna update it for real this time with one that actually works. This is what happens when you just wing it. So maybe that. So C flame, Cassandra 0. Oh, I see. I don't even think you could see the code that I wrote. I'm looking at my terminal now. So this is what I'm writing. So C flame, Cassandra 0 just means, hey, take a flame graph of Cassandra 0. Wall gives me the wall clock profile. And let's only include things that have compaction and stack trace and exclude things that have unsafe park. Do it in reverse. Where's our time spent? I am going to be doing this next week as well. So I'm going to be saving these. One thing that's really nice about this is when I use the C flame command, it automatically downloads these flame graphs to my machine for me. So I actually have everything. If you look here, you might not be able to see this, but it says streaming storage series. That's this. Week 1. So next week, when I start taking a look at the new try indexes, I can actually come back to these flame graphs and we can do a side-by-side comparison and we can figure out exactly what's going on. So it's nice. You can look at the performance differences. And there's actually also diff flame graphs. So that doesn't work. There's nothing out of the box that works with this, but if I were to change the format of the flame graph, then I can do a diff. So we can show, like if you do, let's suppose you were to do a performance, you say, hey, I have an optimization here. you can spin up a cluster. And one of the things that's really cool about this tooling is I built it so that you can deploy custom builds on it too. So you can just point to a Git repo and a branch, and it will build it for you. And I should do a whole thing on how that works. But these are all the builds that are available. So this actually has internally in the AMI that's built. And this by the way, this AMI was built today. This has 5.0 head. So this is the 5.0 branch of the Cassandra. So this is the head of the Cassandra 5.0 release. So for me, it's really exciting. I'm like, yeah, let's just try out the newest stuff, see what happens. But if you have a branch, if you're like, oh man, I have this really cool optimization, you clone the Cassandra repo. It's on GitHub. Make changes, push it up into your own branch, and then you can build your AMI simply by doing this. So if you look here, like this. This is the this is all you have to do. You can download Easycast Lab. It's open source project. I'm not hoarding it. And I encourage everybody to download it. You just go in and you add a single YAML block, and then you run packer build. And there's two things to build. There's a base image that has like a bunch of utilities on it that I like, that are expensive because you have to compile them, because that's just how I roll. And then I build a Cassandra image on top of that image. So if you need to like rebuild Cassandra, like if you're like, oh, I want to try like a bunch of different things, it's really cheap to rebuild the Cassandra image, because it's the base takes about half an hour and the Cassandra image takes like just a minute or two. So you can test your custom patch in if you've already got the base image built, you could go from authoring a patch to a load test in under 15 minutes. That's my that was one of my goals with this project. And we're actually going to be doing some stuff with that in week 4. Cat's out of the bag. Since you stayed with me for an hour and a half, the big reveal. Anyway, so let's see. We have this. Okay, so let's take a look. Oops. I don't actually know which one we're looking at here. Oh no, I must have messed it up. All right, hold on. I'm just gonna redo it, but how did I mess that up? Is it because I spelled compaction wrong? Let's just do this. Let's do everything. I don't have time. I don't have time for this. So now what we're gonna do is just a wall clock profile, and I'll put this here. So one of the things I've been meaning to do is make it easier to take like specific types of profiles, so that I don't go through this error-prone process where I just do it wrong. So that's what I'm doing now. So maybe we'll see something different. Um, I suppose it's possible that there were no compactions running. I didn't see anything um, in the flame graph, so that's why I didn't bring it up. It was empty, and it's entirely possible that was just no compaction work. Um, I probably should have also just triggered a major compaction to guarantee that there was some time spent there. But hey, you know what? Whatever. Live and learn, right? Now you know. Profiling. Here we go. Done. Oops. Okay, rsynced it all. Nice. Okay, I have clearly done something wrong here because these graphs are not giving me anything. Let's just go with one that I know is going to work. I'm just going to do it because I really wanted to. You can add some concepts. Yeah. That's what I'm going to do. Yeah, because a lot of these are like typical. Did I say topical profiles? Uh, yeah, I plan on adding. I plan on adding that. So right now it's running uh, it's running that one right there. It's running that reverse. And if this doesn't work, I have done something horribly wrong. Yeah, the tricky thing is that I guess there's not that much. It's like compaction. Compaction, I want to see wall. Like I don't really want to. I never need a CPU profile of compaction. Sometimes I do, I guess, but generally I want to see wall. The thing I'm most interested right now is to determine what the impact is of compaction on I/O, especially in environments like EBS, where you might use provisioned IOPS and you want to keep your IOPS as low as possible. You want to save some money. All right. Okay, cool. So I have this. This works. So let's share this. Cool. So this is a CPU profile as an isograph. And it's nice because our stuff is at the top and it's aggregated, but it's annoying because there's tons of stuff over here. And so I was really hoping to isolate and only check out. See, like I guess see match 0, so there's no compaction. I should have probably just done the read command. Anyway, but let's say I go here. So this is cool because it's just different, right? It's a different approach. So if the same stuff was at the top, like this is probably our best example here. You can see that we're seeing where do we get few text calls, right? So these are supposed to be cheaper locks, but we actually do a lot of these. So how do we get all these lock calls? Well, this actually comes about because we have the sep worker do wait spin, but we also might see some of it because we have single partition read command. So the question came up the other day when I was looking. This is weeks ago now, but I was looking at something and I was like, hey, we get a lot of few text calls. Why do we have so many failed few text calls? And the answer is mostly because of the sep worker. Is it bad? I don't know. Tough to say. According to this, it does take up 15% of the CPU time. But threads are waiting to be spun down. So they're just sitting there. So however long it takes to spin down a thread, you're going to see it there. So even if it only took a few milliseconds, if you see it a lot, then it's going to be represented in this a lot. But you will actually see a lot of system calls. You will see a lot of system call overhead from this. You can anyway. So maybe we can figure out a better way to do it. Anyway, that's it. That's where I'm calling it. It's been an hour and a half. I haven't had one drink of water. All right. So that's the end of that. I hope that this was interesting. So remember, storage engine overview. We start with mem tables. We move, and commit logs. We move that data into SS tables. It gets compacted together using a compaction strategy of your choice. And then from there, if you want to do a code dive into the code base, I recommend using profiling information to help you narrow down the request. To think of it as like a map. Like, you can still go through the code base. There's nothing that prevents you from going through the code base. However, you will be much better off if you get the profile, because then you don't have to follow every single line of code to get to the point where you say, oh, okay, here's where the read is performed. I actually, so a personal story, before I started using flame graphs, I remember sitting down with someone. I was like, how does Cassandra get to reads? Like, when do we actually get to reads? And I didn't use this. So I was like trying to read through the source. And then it's tricky, because you're like, okay, is it here? Maybe. And then you follow down the wrong path and you go, no, I don't think this is it. No, I don't think this is it. This tells you how it works. So if you want to learn the storage engine, you want to understand where your time is spent, profiling is great. And then you can go ahead and you can get better at understanding this code base. Hopefully someone, hopefully you see this and you're thinking to yourself, I could do this. I can become I can contribute to Cassandra. This is easy. Maybe it was daunting before, but now, thanks, John, super easy. So hopefully you're out there, and hopefully this helped. Dimitri, I assume that you already knew some of this stuff, so maybe all of it, maybe even more. But hopefully, like I said, this was entertaining. Thank you, Sebastian. Really appreciate that. If there's any other stuff that people are curious about, please do the thing where you leave a comment. And I'm on ASF Slack, so I love talking about this stuff. So please reach out. And of course, shameless self-promotion. If you need help, I am where is it? Over here somewhere there, consulting. And I do training both privately and with my Operator Excellence class. So if you want to take your team and be, better, happy to come in and help. I love this stuff. So you're gonna get me at maximum energy trying to teach you how all this stuff works. Thank you for joining. Really, really appreciate it. Have a great rest of your week. I might be chopping up this video and reposting it, but if you watch the whole thing, you don't need to watch any of the other stuff. Thank you very much again. I will see you around. All right, bye.